So to close out chapter 11, looking at two main ideas right here. One is another formula that is in your formula packet, and that's the formula right here for the area of a triangle. Now this does work for any triangle, but we tend to not use it on a right triangle. We would just use it on a non-right triangle because in a right triangle, well, I'll show you why here in a second, but so that this is your basic drawing of a triangle, then whatever angle you know, so we'll call this, let's say we know angle C, where A and B would have to be the two segments that form angle C. So we refer to angle C as the included angle between A and B. So if we just plug those numbers into this, 1/2 AB sine C, so C being the included angle, that's how we get the area of a non-right triangle. You could do it with a right triangle also, but if I have a 90-degree angle right here, well, the sine of 90 is 1, and so 1 times this would just be 1/2 AB. So it wouldn't make sense to use this format for a right triangle. So if you go to this one, if you want to give one a try here, you can see 42 is the included angle. 8.6 and 20.1 are the two sides that form that angle. So if you just plug those into the formula, you get your area to 3 sig figs. Notice that this is in degrees. The rest of what we were talking about for this unit is radians. And so this is the time where you got to be careful when you go back and forth on calculator modes. Make sure you're using the right mode for the right formula. Everything that we've done so far has been in degrees, but you're going to see some formulas here in the second part that are in radians. And so you got to be careful that your calculator is in the right mode. So right here, just a quick reminder on what radians are. Back when you were doing unit circle stuff, unit circle has a radius of 1. And so if this is a radius of 1, if I were to take this radius of 1 and travel that length of 1, I get a radian right here. And so that's where the radians come from. Quick reminder on the conversions. If you are in radians and you want to go to degrees, then you multiply times 180 over pi to get to degrees. If you're already in degrees and you want to go to radians, we multiply times pi over 180 and you get radians. Right here, so a couple practice on conversions. So if I was going to convert 3 pi over 4 radians into degrees, so I take my 3 pi over 4, I multiply times 180 over pi, and we get our 135 degrees. So notice the pi's would cancel, which is what makes that pretty simple. If I'm in degrees already, and I multiply times pi over 180, of course you would reduce your fraction, and you got radians right here. If you're ever not sure as to what you're in currently, oftentimes our book will say rad for radians, just to enforce that you are in radians to start with. If you weren't sure, obviously anytime you have pi, you're automatically in radians. Anytime you have a degree symbol, you're automatically in degrees. If you don't have either one, so if there were no degree symbol and there were no pi, and there was just no hint as to anything as to whether you're in radians or degrees, we assume we're in radians. So just a side note on that. So two formulas that we get, and you check your formula packet on these guys, for the length of an arc. And so that would be this guy right here. So this is an arc length. If you were to stretch that out straight and measure it, that's what we have for the length of that arc. Simple formula for that, it's the angle times the radius. Notice that we are in radians for this, so this is where you got to be careful that your calculator is in the right mode. So here's the angle that's being formed, and if I multiply this angle times a radius, which would be either that guy or that guy, which would be the same length, then I would get my arc length. This is what we have for the area of a sector, and so a sector is simply a part of a circle. And so if we were going to look for this area right here, that would be the area sector, area of the sector. And so again, you got your theta angle from the middle, you got your radius, and so if we just plug that into this formula, we get the area of a sector. So here's a couple practice reps on that if you want to give these a try. But right here, so know the radius is 27, we get the central angle. That's where you see the theta up above. We have a central angle of pi over 3, so it's already in radians because of the pi, so we're safe on that. So if I just do my radius times my angle, my radius times my angle of pi thirds, then we get the arc length right here. If I want the area of the sector, same thing, just a little different formula. Here's the radius, here's the theta, central angle, and you got that right there. This is a great question right here. A really popular IB question is to ask you for a perimeter, and often students aren't really sure what to do with this one. So I'm glad you're seeing this right here in the notes. If they ask me for the perimeter, we'll look at this sector right here. The perimeter would be that radius plus that arc length. And so if I did the arc length plus 2 radii, that would give me the perimeter of that sector. And that's what you're seeing going on down here. So I have 2 radii plus the arc length, and right here we have the exact answer for the perimeter. Give this one a try on number 2. It's the exact same type of problem, just another rep on that. Moving on down here to the last part. This is a very popular IB question right here, looking for this little segment area right there on that piece. So you can see the overall plan of attack right here. If I can get the overall area of the sector and subtract out this triangle, that's going to leave me with that area right there, which is what we are solving for. So that's what you're seeing kind of laid out within the notes right there. So if I'm looking for the area of the segment that you see shaded over there on the right, if we use our formula for area of the sector to start with, so right here we have our central angle of pi over 4. We got the radius of 20. So this is the overall area of the sector. And if I subtract out the area of the triangle, so right here you can see they're doing the 1/2 AB sine C on that. Notice that we're using radians on this one to stay consistent with the problem. Since we're using radians here, we got to use radians here to stay consistent. So if we do a little cleanup, and here's one thing that students often have a hard time with on a test, is they don't remember what this looks like. What is the sine of pi over 4 in radians on a unit circle? And so if you don't remember your quadrant 1 of a unit circle, I would really encourage you to either memorize quadrant 1 of the unit circle for a problem like this, or if you really don't remember it, just draw a right triangle. So if you were to convert this to degrees, right, pi over 4, you would see that that's a 45-degree angle. And so we're saying, what is the sine of a 45-degree angle? You can just create for yourself a little 45, 45, 90, put in your 1 rad 2 format, and you would see that if you did opposite over hypotenuse, you would get 1 over rad 2, which we would clean up to look like this. And so that's another way to go if you don't remember your first quadrant of your unit circle, but this is a step that you need to know how to take, and oftentimes students don't know how to do this. And so, but you do need to know at least one method of converting something like sine of pi over 4 into this ratio here, so that now you can go further with the problem. So now if you clean up as much as you can, that's as far as it goes if we're going to keep things in exact form here. And one more, this one says find the perimeter of the segment. And so a little extra on this one, so we're finding the perimeter of the segment, which means I need this arc length plus segment AB to get the perimeter of the segment. So again, notice they call this a segment. The whole thing right here is called a sector. So be familiar with the vocab on that. But here's the idea, is I need to get segment AB plus the arc length in order to get the perimeter of that shaded sector, shaded segment that you see right there. And so we're starting out with our arc length formula. So we have the central angle times a radius, a radii, and that gives us the arc length, so that's one part of it. And then we're now using a little other information right here to get segment AB. So for this particular problem, one way to approach this, and there can be different methods on this, but if you know that your central angle right here is 2 pi over 3, because this is a radius and this is a radius, and we know all radii are congruent within a circle, when I draw in that height right there for the triangle, I know that I am cutting this angle in half, which means this is now 1 pi over 3, because it's half the central angle. And now I can use a little trig ratio to figure out my x value right here. And then if I double this, I get AB. So that's what you're seeing on this. And so if I use a little sine ratio, because remember the radius is 30, so if I said sine pi over 3 equals opposite over hypotenuse, then that's the setup that you're seeing right here. Just using a little SOHCAHTOA on that. But again, you got to recognize what is sine of pi over 3. So this is where you either have to memorize quadrant 1 of the unit circle or convert this into degrees. Pi thirds is the same as 60 degrees. And so if I said, okay, what's the sine of 60 degrees? Well, draw yourself a little 30, 60, 90 triangle and then use that to figure out with SOHCAHTOA what is the sine of 60 degrees. But one way or another, you got to be able to come up with a method for figuring out that the sine of pi thirds is rad 3 over 2. So again, you either got to memorize that quadrant 1 of your unit circle or use special right triangles to convert from here to here. And so anyway, now if we clean that up, we figure out that x is 15 rad 3. So if I double that, I get AB, which is 30 rad 3. And so that's what you're seeing right here to finish things off. And we got the perimeter of our shaded segment.